Hello, welcome students. I am Rika Thorat, Associate Professor. Today we consider some theorems. Consider theorem number 13. Statement of this theorem is, if H is a normal subgroup of a finite group G, then order of G by H equal to order of G divided by order of H. Such type of statements are asked in for objective questions in exams. Order of G by H equal to order of G divided by order of H. That is order of G by H equal to dash dash, which is equal to order of G divided by order of H. Let us consider the proof of this theorem. Let G be a finite group and H be a normal subgroup of G. Then order of G by H equal to number of distinct right cosets of H in G, which is equal to number of elements in G divided by number of elements in H by Lagrange's theorem, which is equal to order of G divided by order of H. Number of elements of G divided by number of elements of H means order of G divided by order of H. Thus order of G by H equal to order of G divided by order of H. Now we consider next theorem. It is theorem number 14. Statement of this theorem is, every quotient group of an abelian group is abelian. Question on this theorem can be asked as, every quotient group of an abelian group is dash dash. It is abelian. Let us consider the proof of this theorem. Let G be an abelian group and H be a subgroup of this group G. Then H is a normal subgroup of G by previous theorem statements. Now if A comma B belongs to G, then HA comma HB are any two elements of G by H. Then HA into HB equal to H of AB equal to H of BA, since G is abelian. So this property H of AB equal to H of BA is satisfied, which is equal to H of B into H of A. That is HA into HB equal to HB into HA for all A comma B belongs to G. Hence G by H is an abelian group. But from the remark we see that the converse of this theorem is not true. That means if G by H is abelian, then G may be abelian or may not be abelian. That means converse of this theorem is not true. Now we consider another theorem. Statement of this theorem is, every factor group of a cyclic group is cyclic. Let us consider the proof of this theorem. Before seeing proof, objective question can be asked as, every factor group of dash dash is cyclic. Every factor group of a cyclic group is cyclic, or every factor group of a cyclic group is dash dash. It is cyclic. Now we consider the proof of this theorem. Let G be a group. It is G be a cyclic group and A be the generator of G. Let H be a subgroup of G. Since every cyclic group is abelian, therefore H is also abelian. Therefore, H is a normal subgroup of G. Now let X belongs to G. But since G is cyclic group generated by A, therefore X equal to A raised to N. G is cyclic group generated by A means X equal to A raised to N, where N is some integer. Then Hx is an element of G by H. Now Hx equal to H into A raised to N, which is equal to H into A dot A up to N times. And this is equal to HA dot HA dot HA up to N times, and which is equal to, in bracket, HA bracket raised to N. Hence, Hx belongs to G by H. That means quotient group. This implies Hx equal to HA raised to N, where HA belongs to G by H. Thus, G by H is a cyclic group generated by HA. This can be also asked that G by H is cyclic group generated by dash dash, that is HA. There is one remark. The converse of this theorem is not true. That means cyclic group will not be a factor group. It may be factor group or may not be factor group. Cyclic group may or may not be a factor group. That is, converse is not true. Thus here we have seen that one statement, that is order of G by H equal to order of G divided by order of H, where H is normal subgroup of a finite group G. That means order of G means number of elements in G divided by number of elements of H, which is equal to order of G divided by order of H. That is, order of G by H equal to order of G divided by order of H. And here we also consider the definition of quotient group or factor group. That means definition is H is normal subgroup of group G, then the set G by H of all cosets of H in G forms a group under the multiplication of cosets. This group is called as factor group or quotient group. Here H must be normal subgroup of group G. And we considered here theorems on factor group and quotient group. Also, first we see normalizer of an element. Normalizer means group G be a group and A be any element of this group G, then NA equal to set of all X belongs to G such that X equal to X. It is called as normalizer or centralizer of A in G. That means for objective G be a group, then the normalizer of an group NA equal to dash dash. That means XA equal to AX, or NA equal to set of all X belongs to G satisfying property XA equal to AX is known as dash dash normalizer or centralizer of A in G. Then we consider one theorem, that is center ZG of a group G is normal subgroup of a normalizer of an element. Here we consider ZG as a center of group, and then we consider Na as normalizer of an element in G, and we consider any element belongs to ZG and it also belongs to Na, since here property xa equal to ax is satisfied for all A belongs to G. Thus Zg is contained in Na, that is Zg is a subgroup of Na. But Zg is normal subgroup of G. Hence by previous theorem Zg is a normal subgroup of Na. Then we consider one theorem on factor group and quotient group, and we prove that G by H is a group under binary operation defined by HA dot HB equal to H of AB. For group, we consider that G by H satisfies all the properties, that is closure property, associative property, existence of identity and existence of inverse. Here G by H, elements of G by H are HA, HB. So that for closure property we prove that H of HA dot HB is equal to H of AB, and H of AB belongs to G by H of AB belongs to G by H. So G by H is closed with respect to multiplication. In second property, H of A into H of B into H of C equal to H of AB into H of C. That means associative property is satisfied, existence of identity is also satisfied, that is HA into H equal to H of A into H of E equal to H of AE equal to H of A also. Here HE equal to H is considered as an identity element. And for last property of group, that is existence of inverse. If HA belongs to G by H, then HA inverse also belongs to G by H. Here HA into H of A inverse equal to H into HAA inverse equal to HE equal to H. That means HE equal to H, and HA inverse into HA is also equal to HA inverse into A equal to HE equal to H also. That means HA inverse is inverse of HE, that is HA inverse equal to H into A inverse. Thus all the properties of group are satisfied here, so that G by H is a group. All the properties of group are satisfied by G by H. Hence G by H is a group with respect to multiplication. And then we consider quotient group, factor group, one remark, and we prove that every quotient group of an abelian group is abelian. But converse of this theorem is not true. And also we consider one theorem, that is every factor group of a cyclic group is cyclic. And here also we get one remark that converse of this theorem is not true. That means if the group is cyclic, then it may or may not be a factor group. That is converse of this theorem, every factor group of a cyclic group is cyclic, is not true in every case. That means in both this theorem, theorem 14 and theorem 15, converse is not true for both these theorems. Also we considered one important theorem, that is, if H is normal subgroup of a group G, then order of G by H equal to order of G divided by order of H. Thank you.